Hey guys, this is Sergey, and you're watching Dissecting the Code. Today I want to cover LINQ, something that almost every .NET developer uses, but not everyone understands. And in order to understand LINQ, I want to cover IEnumerable, a foundational building block. And understanding IEnumerable is super important to understand why the LINQ behaves the way it behaves. Okay, what is LINQ? LINQ is a unified API for processing data from various data sources in a declarative way. Since there are multiple data sources, there are multiple types of LINQ. A typical one, the one that we are going to cover today, is so-called LINQ to objects. It's based on IEnumerable and is designed for processing collections in memory, collections or sequences that we can generate on the fly. Another variation is LINQ to entities, and previously it was called LINQ to SQL. It's based on IEnumerable, and it is designed to process data from databases. And there are a few other options, like LINQ to XML, async LINQ, which is based on async enumerable, or LINQ over reactive extensions, that is based on IEobservable. LINQ is language integrated query, and by integrated it means that we can use SQL-like syntax inside C# code. Another variation of LINQ is so-called fluent syntax, where we can use .where.select to essentially get the same behavior as with query expression syntax. Typically, when we deal with collections in memory, I find that most people are actually using a fluent syntax instead of query expression syntax. But you should remember that query expression syntax is just a syntactic sugar, and compiler just translates between one version to another. In order to understand LINQ, we should understand IEnumerables. And IEnumerables is an implementation of Iterator design pattern that was popularized by a famous design patterns book published in 1994. The idea of the iterator is that it allows accessing elements of an object sequentially without exposing its internal structure. In .NET, it is represented by two interfaces. The first one is IEnumerable. Every collection implements IEnumerable, and it means that a collection or a thing can be enumerated. The main method there is called getEnumerator that returns an IEnumerator. You can think of iterator as a pointer inside of the collection. And every implementation of iterator design pattern has a few key members. The first one is a current property that allows accessing the element from the collection. Another one is moveNext. It allows moving the iterator to the next element. And if moveNext returns false, it means that the iterator reached the end of the collection. And enumerator in .NET also has two other methods. The first one is dispose, which is used for releasing managed resources associated with the iterator. And the last one is reset, which is actually not always implemented, so please don't call it, and it is used for resetting the position of the iterator to the start of the collection. And you can think of iterator as a state machine, and we'll see in a moment why it's so important. Let's say that we have a list with 3 items. We get the enumerator. When the iterator is created, it kind of points to an element before the first item. It means that accessing the current item is actually undefined. We need to first call moveNext, and that moves the pointer to the first element. In this case, moveNext will return true, and the current item will be 1. The next time we call moveNext, the iterator will point to the next item, and the current item will be 2. When we call moveNext the 4th time, the result will be false, and it will indicate that iterator is finished, and accessing the current item is also undefined. The key point here is that the initial state of the iterator is actually undefined, and we need to call moveNext in order to access items from the iterator. But it is very important to understand how Foreach is implemented under the hood. Technically, Foreach in C# uses duck typing, and it does not require the collection to implement IEnumerable or IEnumerable of t. And here what the compiler does under the hood to translate Foreach into lower level instructions. We can use ilspy or sharplab.io or resharper ilviewer to see the lowered version of C#. The compiler translates Foreach into the while loop. It first gets the enumerator out of the source, and it immediately calls moveNext before accessing the items. And when moveNext returns false, or if the exception will occur in the try block, the finally block is called. And finally block calls dispose on enumerator, and we'll cover in more details why it's super important. And even though it's not very hard to implement getEnumerator by hand, typically we use C# language features called iterator blocks. Iterator blocks are generated by the compiler if the return types is something like IEnumerable of t, and the body of the method has yield return, yield break, and other statements. Having yield return in the method body tells the compiler to generate a state machine used for a custom iteration. Let's look at 2 simple cases. Let's say that we want to implement a custom read-only list that wraps a list of t, that exposes a few things like count and getEnumerator. And getEnumerator implementation is quite trivial. We'll for each over a list and we'll yield return each item. The same is true if we want to create a range iterator that will generate the data on the fly. We'll take a start and end the count, and then we'll have a for loop where we'll yield the data that will be consumed when this iterator is consumed. There are a few rules that converts a regular method into an iterator block. First, the return type should be IEnumerable of t or IEnumerator of t. Actually, non-generic versions are supported, but this should be very rarely used. Yield return x sets the x as the current value of the iterator. When the iterator will reach to this point, that's the value that the current property will return. Yield break completes the iterator. You can think about this as an early return, and in typical methods we use return, but we cannot use return here. We need to use yield break. And keep in mind that not the result type of the method forces the compiler to generate the state machine. That's what forces the compiler to use a different code generation logic. Before looking at how iterators looks under the hood, let's just look at how they behave. Let's say that we have a very simple iterator method. It has two yield return statements here, so it means that it generates a sequence with two items. When we call this method and obtain an enumerator, no code is going to be executed. So in this case, the iterator state is still undefined. So when we will call current, we will get 0, but technically an exception can be thrown and whatnot. In most cases, we'll get the default value of the type of t. In this case, it's int, so we'll get 0. When we call moveNext for the first time, this is the time when we actually start executing the code inside of iterator method. So we will see step 1 being printed, and the current item is 1. When we call moveNext for the second time, we will run the code from the last yield return to the next yield return. It means that we'll see step 2 on the screen, and the current will be 2. When we'll call moveNext for the third time, we will run the code from the last yield return to the end of the method. We'll see step 3 being printed on the screen, and moveNext will return false. And in this case, accessing the current item is again undefined. And now let's see what the compiler does to achieve this behavior. We have the same iterator method. The compiler generates a private type with d__0, and this type implements both IEnumerable and enumerator. It has a few fields. The key ones are the state and the current item. The state is very important because it shows how the state machine actually works. And here we can see how iterator method is translated by the compiler. So now it doesn't have any code that we see here. Instead, it creates this generated state machine and passes -2 as the current state. So our original state is -2. And when we call getEnumerator to consume this sequence, this is the place where the state changes from 2 to 0. It has a few extra checks, like it checks if the current thread is the thread that created the state machine, but we can ignore this information. At this point, we got the enumerator, but nothing from our code was ever being executed. This is what moveNext does. Actually, moveNext method is the place where all of our logic now sits. When we first call moveNext, we check the state, and if the state is 0, it means that we're calling moveNext for the first time. First, it will set the state to -1, which is only needed for exception handling, and then we'll run the code from the start of the method to the yield return, and we set the current item to 1, which is equivalent to yield return 1. And that's why when we call moveNext for the first time, we will see 1 being printed on the screen, and the state will be changed to 1. And when we'll call moveNext again, the state machine will check that, okay, now we need to run the code between the first yield return and the second yield return. And the same will happen when we call moveNext again. In this case, the state will be 2, and we will run the code after the second yield return to the end of the method. And will return false, indicating that the iterator is finished. And this is the final state of the iterator. And -1 is a special state. If we call getEnumerator again, we will essentially restart it and start from scratch. And let's benchmark the state machine to better understand the implementation details. First of all, our state machine is a class. It means that every time we iterate over it, we should see at least one allocation. And it is very intentional. The generated state machine implements two interfaces, IEnumerator and IEnumerable. And it means that it can be used as a collection or a sequence, and it can be used as an iterator itself. Let's check two cases. We will consume iterator once, and in the second case, we'll consume iterator twice. Theoretically, the iterator should be reused and the amount of allocated memory should be the same. And this is exactly what we are seeing here. The time increases, which is reasonable, but the number of allocations stays the same. And we can use my open source project called Object Layout Inspector to see how exactly a generated state machine laid out in memory. First of all, when we get the enumerator, we can print its own layout, and then we can get enumerator and print the layout. And the actual type is exactly the same. This is a generated state machine. The benchmark shows that we have 32 bytes of allocations, but the actual data size of the generated state machine is just 16 bytes. That's because every heap allocated object has two extra fields, method table pointer and object header. That's why even an empty class allocated on the managed heap will take 16 bytes of memory. And the compiler can reuse the iterator instance. It's because when it finishes, it sets its state to -1, and so when the next time we call getEnumerator, it can start from scratch. It's funny that the reset method is actually not supported by the generated state machine, but you actually can iterate over a generated sequence more than once. Let's recap what we know about iterator blocks so far. First of all, they're kind of resumable execution based on the generated state machine. The return type should be either IEnumerable or IEnumerator, and yield return is used to produce the next item. And calling a method just creates an iterator. No code is going to be executed in this case, and each step is executed when the move next is called. Let's look at a more complicated example. Let's say that we have a method called iterator that takes a seed, and we want to make sure that this seed is not negative. So we can enforce this by using argument out of range exception throw if negative. And here's how we're going to consume this. So first we will call an iterator method inside the try-catch block, and then we'll consume it and just print the sum. So what is going to happen when we run this code? Are we going to print the error message and that's it or not? So we get an unhandled exception. So instead of printing the error message and exiting the execution, we're actually getting an unhandled exception. And the unhandled exception is coming from the iterator block where we call the sum method. So instead of failing here when the method is called, we failed when the iterator was consumed. So let's recap what's going on. Yield return-based sequences are lazy. So when the method is called, we're just getting IEnumerable, and we can think about this as a promise to produce the data when the data is consumed. Because as we know, when the method is called, no code is being executed here, and the code is only executed when the iterator is consumed by calling the first moveNext method. And moveNext is called for the first time here, not here. So what's the fix? The fix is to extract the iterator block into a helper method. Our original method will eagerly validate the arguments and call a nested method. So when this method is called, we will immediately execute the argument validation logic and throw the exception eagerly. And only after that, we will call the iterator block and produce a lazily generated sequence. And now let's cover another interesting case, the resource management. So we know that iterator implements idisposable, and for each loop calls dispose on it. But why? Let's change our iterator a bit. Let's say that instead of just writing to the console, the first line in this method acquires the resource, and then in the finally block we release the resource. We can use try finally block, or we can use using statements and whatnot. And let's see what's going to happen in this case. So let's say that we call this method and get enumerator out of it. We know the drill right now. When we call getEnumerator, no code is being executed and no resources were acquired. The resources are going to be acquired when we first call moveNext. That's why we see calling moveNext1 and then acquiring the resource. And this is the place where we compute the current property. When we call moveNext again, we executed the code between yieldReturn1 and yieldReturn2. And when we call moveNext the third time, we'll execute the code after the yieldReturn2 to the end of the method. And this is where we'll release the resources. This is fine. It means that we actually will release resources when we reach the end of the iteration. But what will happen if we'll abort the iteration in the middle? Let's compare this to the case when we call moveNext only once. We'll acquire the resources and that's it. We will never release the resources because the iterator was never disposed. And this is the reason why the for each loop is implemented the way it is implemented, and always call enumerator.dispose if it was obtained. In this case, if the exception will happen in the loop, the dispose method will be called and the underlying resources will be freed. Now we have a good understanding of how IEnumerable works. Let's put this in practice. Let's say that we have a public method called processData that takes IEnumerable of string. Let's say that it traces the number of items using structured logger, and then it uses a for loop to iterate over the sequence. It goes from 0 to data.count, and then it gets the ith element using data.elementAdd. It parses the value, logs the results, and at the end it logs that the processing was done. And let's say that for years we've been using list of string as the input for this method. Let's benchmark the current implementation. We'll be targeting .NET 8 and we'll be using 3 different input counts, 10, 100, and 1000, just to check that the algorithmic complexity is correct. And these are the results. Maybe they're not perfect, but they're definitely reasonable. It is very unlikely that anyone would ever notice any performance problems with this code. The complexity is linear, we have 0 allocations, so technically we have 0 problems with this code, right? But what if someone, at some point, will change the actual type from list of t to IEnumerable? And now, all of a sudden, everything breaks. The time goes up quadratically. Instead of a linear speed, now we actually have a quadratic complexity, and we have a whole lot of allocations. And benchmark.net shows that for 1000 items, we have 22 megs of allocations, and the allocations are so much higher than for the other two cases that the benchmark.net incorrectly shows that the other two cases had 0 allocations. Let's look at the code again, and this time let's enable one of the static analysis rules that shows a possible multiple enumerations. And we can see that we have a lot of them. So why the behavior is so much different? Let's just think about how data.count or data.elementAdd could be implemented under the hood. If the underlying type is a collection or a list of t, the LINQ might, and it does, have an optimization to get the count property or just to use an indexer. But if the source is actually an IEnumerable, then the only way to get the count is to iterate through the whole collection. And the complexity here is quadratic because on each iteration of our for loop we call data.count and data.elementAdd. And these two methods have a linear complexity. The biggest problem of this code is that it is not possible to reason about the algorithmic complexity of this method just by looking into it. You need to know how this method is used. And it's possible that for many years this method was used with list of t or other collections, and at some point the input might be changed to be an actual IEnumerable because the types are compatible, drastically affecting the application performance. A lot of misconceptions about LINQ, like LINQ is slow or it's error-prone, comes from the fact that not everyone understands how IEnumerable works under the hood. And this is what we've been covering today. And that's why LINQ might be tricky, because the semantics of IEnumerable is not clear. Is it a collection in memory? Is it a remote code execution because you're using LINQ to entities? Is it a local query with side effects? And since LINQ is used by millions of developers, it has a ton of optimizations. And for instance, count and IEnumerable are optimized for a list of t or for collections. And when the actual type changes over time, that changes the algorithmic complexity of those operations. And that's why I'm not a big fan when IEnumerable is used in public API. It's very hard to implement those public APIs correctly. What's going to happen? Are there going to be any side effects? I typically tend to use it as an implementation detail. In many cases, LINQ laziness is a feature, not a bug. But when IEnumerable interfaces are propagated between modules, it becomes very hard to reason about the overall application performance. One might think that enabling this static analysis rule might be a good idea, but in practice, if you'll try to enable this on any reasonable codebase, you will get so many false positives that I don't think that it's going to be a good idea. Unfortunately, there is no way to catch those errors that truly will cause a quadratic complexity, where the possible multiple enumerations are happening in the loop. That's it for today, guys. Thanks for watching, and see you next time.